Thermodynamic relations. So now we are going to discuss about the thermodynamic relations of the principle of exact differential. When generally when point is a function of 2 points, okay, z is a function of 2 points, okay. So how can we, if we differentiate z can be written as dou z by dou x at y, putting y constant, differentiation of z function z with respect to x, putting y constant, into into dx plus differentiation of z with respect to y, putting x constant dy. Okay, so comparing with dz equal to mdx plus ndy, so dm will go to dou z by dou x at y constant, n equal to dou z by dou y. Okay, we'll get one relation condition for the exact differential, that is a property. So generally Maxwell derived the I think 4 equations. Okay, so you don't need to remember all the derivations, but just remember the shortcut which I will discuss later. Okay, TdS equal to du plus pdv. Remember this equation to derive first relation. TdS equal to dh minus vdp. You remember this equation. And okay, so now du equal to TdS minus pdv. Compare with the equation dou z equal to mdx plus ndy. Okay, you will get just remember the proper condition for the exact differential, apply it, you will get the relation. Similarly, you apply for the second one. Okay, so Gibbs function can be given as g equal to h minus ts. If we differentiate it, we will get one relation, and dh minus tds equal to dh minus tds is vdp. So again you apply the condition for the exact differential, you will get one relation. Similarly, f equal to u plus ts. This is known as Helmholtz function. Okay, so again you in the place of u, if you differentiate du minus tds equal to minus pdv, you will get another relation. So generally when we discuss about the shortcut, you just draw one square. Okay, Pawan sir is very talented. Okay, p starts from right corner. Okay, p s v t. Okay, so generally when the arrow is coming downwards, when the arrow is negative y, then it will be negative. When the arrow is positive y, then it will be positive. In a negative x, positive x, whatever it may be, that will be positive. Okay, so generally again when the arrow traveling from p to s, from downward also it must travel from t to v. Okay, these 3 points you remember. And dou p by dou s at constant volume equal to dou t by dou v at constant s. Okay, again if you want to put the signs, the arrow is coming downwards, so you can put negative at dou p by dou s at v. All right, so again for the 4 relations, next dou s by dou v at t equal to dou p by dou t at v. So positive x, negative x, so don't need to put any directions. All right, again if you want vtp, okay, dou u by dou t at p, again dou s by dou p at t. Okay, arrows must travel at same direction, you will get the relation. Okay, so upward is if arrow is upward, that is positive y, it is positive, negative y, it is negative. Okay, all right, so next is partial derivative theorem. Okay, cyclic integration. So generally if z is a function of x and y and z, okay, that equal to 0. Okay, so how can you write, you generally draw one cycle. Okay, xyz, xyz, xyz. Okay, xyz, dou x by dou y z, dou y by dou z x, dou z by dou x y equal to -1. But in our thermodynamic variables, present temperature and cyclic relation is given by pvt, pvt, pvt. You write like this. Okay, pvt, then dp by dv of t, dv by dt of p, dt by dp of v equal to -1. Okay, so for ideal gases, generally you just write for the ideal gases. Okay, find p equal to mRT by v, right? You differentiate p with respect to v at putting t constant. Okay, and you do similarly do, and you just multiply all this, you will get -1. Okay, this is one of the basic thing. TdS equation, from the exam point of view, he told that just derive some equations yourself before examination, so that if any problem comes you can do, but this is not that much important. Okay, so TdS equation, we need to derive TdS equation. Alright, so TdS equation we are deriving in terms of constant volume, case 1, in case 2 constant pressure, and case 3 we are deriving Cp minus Cv equal to R, you know, right? So where does it came from? Cp minus Cv equal to R. It came from thermodynamic relation. Okay, Cp minus Cv equal to minus T dou V by dou T of at P whole square dou V by dou V of T. Equation number 4. Okay, all right. So if you substitute dV by dt, just find V equal to mRT by P. mRT by P. Okay, dV by dt at constant pressure, just find, and dP by dV at constant temperature, you just find, and just put it in this equation, you will get R. Okay, again TDS equation. So entropy is a function of temperature and volume, right? So temperature and volume, temperature and pressure. For constant volume we are taking volume, right? ds equal to ds by dt of V at T dt. That's ds is find. Okay, T ds by dt, where does it came from? It came from the slope of the constant volume process, and the slope of dt by ds equal to T by Cv. Similarly, for constant pressure, dou T by dou S equal to T by Cp. Okay, you will get these two relations. Remember this two relation, and certain manipulations in the data you will get. There are certain doubts which I got was, first of all, T equal to function of pressure and volume, right? We are taking this. Okay, and by comparing the coefficient of dP, you will get P here and V here, because you are comparing dP. Okay, dP by, if you compare dP in dt by dou P at V. I'm not talking from the notes, just look at the notes. Again, you will get T by Cp minus Cv dou T by dou T of P. Okay, Cp minus Cv you will get from cyclic relationship. And next dot which I came there, just we are dividing, right? So why we are getting minus dou P by dou V at T, dou P dou V by dou T. Generally when you look at dou T by dou P, he reversed it. Okay, so he divided it. Okay, alright. So here temperature will be positive in equation number 4. Dou T by dou P is positive, and dou P by dou V. In compression process it will be negative, expansion process it will be negative, putting temperature constant. So Cp minus Cv will come as positive. Cp is greater than Cv, gamma is greater than 1. Alright, so this was